Okay, same question, population here. Here's the equation for it. Before, what we did is we found the slopes before 15 and after 15, because we're looking at when we're looking for the estimated instantaneous rate of change when we're 15 years past the year 2000. Another way to do it is, instead of looking just before it, so like we said, we looked for t at 14 and 15 slope, then we looked at t at 15 and 16 for slope, and then we added the two together, divided by 2, and that was our estimated. In this case, what we'll do is we'll find two values around 15. So for instance, instead of doing 14 to 15, we can use 14 and 16, because we know 15 is going to fall right in the middle of them. But to be more accurate, it's technically best to get closer to 15. So for instance, we could use t at 14 and 16 like we said, but that's a gap of a solid 2 years. You know, our estimate could be close, but we can become more accurate. We might want to use something like maybe 14.5, which is only a half year away from 15, and 15.5, which is only halfway a year away from 15. Or to get very accurate, we might want to use 14.9 and 15.1. And you see how the closer and closer I'm going to get using these two terms, the more accurate my estimate is going to be for the instantaneous rate of change at year 15. Okay. Now in this one, instead of calculating two slopes, we only have to calculate one slope. Okay. So what we'll do is we'll calculate the one slope very quickly here. I think they've actually given it to us in 15. Discovered what they've done is at p at 14.5, we'll just write the values in and then find the slope, are 74559, and p at 15.5 is 71009. Well, those are our two coordinates, our x1 and y1, x2 and y2. We just got to find the change in y over change in x, and it turns out it ends up being the exact thing we had found before, being 3,550. Okay, so those are essentially the two methods you can use for instantaneous rate of change.